You see, there is one topic which I have not discussed. Is about this rate of change here. Yeah. So this is also an important topic for your test one. So that's what I want to discuss this morning. Look at some examples about rate of change. Yeah. And after that, I will continue with the lecture on multiple integrals. So this is what I want to discuss first this morning. Some examples are related to rate of change. Yeah? This is included in chapter 1, um, but which I have not discussed yet. Yeah. So even in this Dr. Yusuf's book, there is a topic here about rate of change. Yeah, rate of change. Okay, which I have which I will discuss this morning here. So the rate of change, the formula is given before. Let me show you where that formula is. Yeah, this one here. Uh, this one here. This formula is given before. And this formula is related to rate of change. Okay, so recall this formula. So if we have z of a functions of two variables, x, f, x, y, and x and y are in terms of t, then z as a whole is a function of t. So we can find dz dt. So by the chain rule, dz dt is z partial x times dx dt plus z partial y times dy dt. See? So in applications, normally t refers to time, time. So we expect how the rate of change of quantity with respect to time. So let's see an example. Suppose we have a right circular cylinder is changing in such a way that its radius r is increasing at the rate, say 3 centimeter per minute. Okay, so and its height h is decreasing at the rate um, of 5 centimeter per minute. Yeah, at what rate? Yeah, the question is at what rate is the volume of the cylinder uh, changing when the radius is 10 centimeter and the height is 8 centimeter. is 8 centimeter. Okay. Yes. So a right circular cylinder, um, it is, let me make a sketch. Yeah, this is a simple sketch of a cylinder, and it has a base, it has a height here h, and radius r. Radius r. What is given? It's given that the rate of change r here is increasing. So the RDT here is increasing here. The RDT, what is given, 3 centimeter per minute. Yeah, 3 centimeter per minute. So the radius is increasing. Yeah, but the height is decreasing. Yeah, the height here is decreasing at the rate of, because it is decreasing, we put a minus sign, minus 5 centimeter per minute. Okay, if it is increasing, we give it a positive sign. If it is decreasing, we put a minus sign. So we want to know dVdt. Yeah, what is the rate of change of dVdt, the volume of the cylinder at the measurements radius equal to 10 centimeter, and the height is r centimeter. Okay, what is the relationship between V, R, and H? Yes, can anybody tell me relationship? Pi r square. Yeah, volume. The volume is pi r square h, right? So we can think of V as a function of R and H. Yeah. So dVdt, okay, by the chain rule, shown here. Now the rule of Z is V, the rule of X is now R, and the rule of Y is now H. Yeah. So by the chain rule, dVdt is V partial R times dRdt plus V partial H times dH dt. Okay, look at the symbols that I have used here. Okay, there are some derivatives with straight D, and some derivatives with curly D. Okay, so make sure you use the correct symbols here. Even this, carry marks in the test or in the finals. So I've seen in some of your assignments. So when you use the chain rule, you did not pay attention to the correct use of symbols. Yeah. Sometimes there are some assignments that students use all derivatives with straight D. Yeah. So please write down this. When you apply the chain rule, please make sure you use the right symbols here. So this is the right symbols, notations for dVdt. So what is the V partial R here? V partial R is what?
2 pi RH.
2 pi RH, yeah. 2 pi RH. dRdt is given as 3, and V partial H is
Pi R squared.
pi r squared, yes. Pi r squared, and dHdt is minus 5, yeah, minus 5. Okay, so we want to find dV, the rate of change at a time or at the moment where uh, R is equal to 10, yeah, and H is equal to 8, yeah, yeah. So we substitute in the above result, replace R by 10 and H by 8, so you get 2 pi 10 times 8 times 3 plus pi R squared. R squared is 10 squared times minus 5. Okay, then we simplify this. What is this? We have 3, 824, 240, 480 pi, right?
Yeah.
The first term is 4 pi is then minus 500 pi, which is minus 20 pi, right? 20 pi. Yeah. So the unit here is centimeter cube per minute. Okay. So we have a negative sign here. So that means what?
Decreasing.
Decreasing. Yeah. So that means uh, at this measurement, the volume is decreasing at the rate of 20 pi centimeter cube. Okay. So this means that the volume is decreasing at the rate of 20 pi centimeter cube per minute. Okay. Yeah. Any question for this example? Okay, let's look at another example. Um, this one is a problem related to fluid. Yeah. The time rate represented by Q or flow of fluid through a cylindrical tube uh, with radius R and length L is given by this formula here. Q equal to pi P R to the power of 4 divided by 8L eta here. Yeah. So this is a function of Rn, Rn, Rnp, Rnp. Yeah. Where the eta is viscosity of the fluid. What happened here? What happened here? Accidentally touch something here. Eight L eta, where eta is a quantity for viscosity of the fluid, And then P here is the difference in pressure. Difference in pressure at the two ends of the tube. Okay, so example, we have a cylinder here, like a windpipe. So water is flowing, right? Water is flowing. So it has a length L, and also this some radius R here. Okay. So this is related to fluid mechanics. Yeah. Yeah. So suppose the radius increases at the rate of 1/10, and the pressure decreases at the rate of 1/5. Okay. Find the rate of change of Q with respect to time t. Okay. So we are given what? We are given, according to this question, 1/10 refers to what?
0.1.
How to write the in terms of symbol to represent 1/10? It's radius. So how to write 1/10 in term as a symbol?
dRdt.
dRdt, yes, dRdt. dRdt equal to 1/10. What else is given? 1/5.
dP
To
dt.
write them, dP dt, yeah, dP dt is decreasing, right? The
Yeah,
pressure. So should it
negative.
be 1/5 or minus 1/5?
Minus
Minus 1/5, right? And we want to find, what is it that we want to find?
Q with respect of T.
Yeah,
dQ
dQ
dt.
dt. Okay, this is what we want to find. So Q is a function of R and P here, right? So by the chain rule, dQ dt is Q partial R times dr dt plus Q partial P times dP dt. Okay, this is what uh, the chain rule for formula for dq dt here. So what is Q partial R? We want Q partial R. What does it? What is Q partial R?
4 pi r 4 pi p r cube.
Uh-huh. Divided by 8 ln, right?
Yeah,
So okay, let me write it down here. What is Q? Q is pi p r to the power of 4 over 8l eta. This is the Greek symbol eta, yeah, eta. So Q partial R is 4 pi p r cube over 8 L eta. The RDT is 1 over 10. Okay, what is Q partial P?
pi
Q
r
partial P is pi
power 4.
pi r to the power 4 over 8L eta. And the PDT is minus 1 over 5. So the next step is just to simplify this. So when you simplify this, we will get 4 over 8 is 1 half. 1 half times 110 is 20. So we have 1 over 20 times pi p r cube over L eta. Then we have minus, isn't it? Minus 1 over 40. 1 over 40. Then we have pi r to the power of 4 over L eta. Yeah. So let's simplify this. We can factor out pi ln. We can also factor out r cube, isn't it? R cube. We can also factor out 40. Yeah, we can also factor out pi. That's r cube. Cannot factor out p. Let's factor out 40 L eta. So what's inside this bracket here? We have 2p, right? 2p inside this bracket minus r, isn't it? Minus r, yeah. So that is the rate of change of p. That depends on r, L, eta, and p. So if the quantities they are given, then we just substitute into this formula, right? Into this expression. So we leave it in this form. Any question? Okay, another rate of change of formula is one that has three variables, a function of three variables here. So let's see an example of that the rate of change involving functions of three variables. All right. As an example, let's consider this related to electricity. The combined resistance resistance R produced by three variable resistances denoted here by R1, R2, R3 connected in parallel is modeled by the formula uh, 1 over R equal to Do you know what that formula is?
1 over R1 plus 1 over
Yes.
R2 plus 1 over R3.
Yes. So you have learned about this, huh? Where do you know? Where did you learn about this?
Circuit theory.
Physics? In physics?
Yes.
Okay. Yeah. So electricity engineering, electrical engineering student, they should know this. Yeah. And suppose at a certain instant, um, this is a problem from a calculus book, an exercise problem. Yeah, this problem is taken from a calculus book in the exercise. Yeah. So let's solve this exercise problem. R1 equal to 100 ohms, R2 equal to 200 ohms, R3 is 300 ohms, 300 ohms, and R1 and R3, they are decreasing at the rate of at the rate of 2 ohms. No, 1.5 ohms per second, while R2 is increasing at the rate of 2 ohms per second. Yeah. How fast is R changing at this instant? How fast is R changing at this instant? And then is it increasing or decreasing? Is it increasing or decreasing? So that is the question here. All right. So we can think of R here as a function of three variables, R1, R2, R3. Okay. So here R is a function of three variables, R1, R2, R3. What is given? 1.5 represents what? 1.5 ohms per second represent
dr dt.
the R1 dt. Okay. And R1 and R3 are decreasing at the rate of 1.5. So that means what? D R1 dt as well as D R3 dt equal to 1.5
1.5 ohms
1.5.
per
Minus
second.
1.5.
minus, yes, minus, because it is mentioned there R1 and R3 are decreasing, okay, at the rate of 1.5. Yeah. What about 2 ohms represent what? D R2 dt.
DRT.
Is it plus 2 or minus 2?
Plus 2.
Plus 2, yeah, because it is increasing there. Okay, what is it that we want to find? We want to find d r dt. Okay, d r dt at the instant where R1 is 100, at the instant at the instant where R1 is 100, R2 is 200, and R3 is 100. Yeah, this is what we want to find. So we apply this chain rule formula, okay, shown there. But we use the the symbols accordingly. Yeah. So by the chain rule, d dr dt is r partial r1 times dr1 dt plus r partial r2 times dr2 dt plus r partial r3 times dr3 dt. Okay. Now, how to find these partial derivatives? What is the, you are given 1 over r. Okay, how to find these partial derivatives? You are given 1 over r equal to 1 over r1 plus 1 over r2 plus 1 over r3. One way is to solve for r, right? One way is to solve for r. Then what do we get? Write everything as a single ratio. Then upstairs here we have R2, R3 plus R1, R3 plus R1, R2. So therefore, if we now take the reciprocal, R is R1, R2, R3 divided by R2, R3 plus R1, R3 plus R1, R2. Okay, this is one way. And then we find R partial R1, R partial R2. But there's an easier way actually. There is an easy way. Okay, instead of working with this formula for R, why not take the partial derivatives straight away from this equation with respect to R? Yeah, so alternatively, we differentiate both sides with respect to R. What is we want to differentiate? We want to find R partial R1. Yeah, R1. Differentiate both sides. Take partial derivatives of both sides with respect to R1. What is on the left? 1 over R is, this is R to the power of minus 1. This is R1 to the power of minus 1. This is R2 to the power of minus 1. This is R3 to the power of minus 1. So use chain rule. It is minus R minus R to the power of minus 2 times R partial R1, right? Using the chain rule, yeah. And on the right, the first partial is minus r1 to the power of minus 2. And the rest is 0, isn't it? Yeah. The next two partial derivatives are 0 because 1 over r2, because here we don't have r1 here. So the derivative with respect to r1 is 0. And for the third expression here, third term, it's just 1 over r3. There is no r1 there. So the partial derivative is 0. So therefore, we have r partial r1 equal to, what is it? 1 over r squared. This is a minus sign, cancel out. So this is like r squared over r1 squared, right? Yeah. Okay. So similarly, we also get r partial r2 is equal to r squared over r2 squared. And r partial r3 is also r squared over r3 squared. Yeah. So now substituting all this result into the chain formula, substituting where? Here, yeah, substituting in this formula here. Into here. Okay, so on the left is so dr dt r partial r1. What is r partial r1? R squared over r1 squared, and dr1 dt is what? Dr1 dt is
Negative 1.5.
minus 1.5. Yeah, minus 1.5. And r partial r2 is r squared over r2 squared, and dr2 dt is 2, right? And r partial r3 is r squared over r3 squared, and dr3 dt is minus 1.5. Yeah. Now, what is, we know r1 squared, right? We know r1 squared. But what is r? Given r1 is 100, right? 100. So, what about r2 is 200, r3 is 300. So 1 over r, 1 over r is 1 over r1 plus 1 over r2 plus 1 over r3 is equal to 1 over 100 plus 1 over 200 plus 1 over 300, which is 0.01 plus 0.02 plus 0.03, which is 0.06. So therefore, r is 1 over, take the reciprocal, which is 600. Yeah, 600. So going back to this formula, so therefore dr dt at the instant where, at the given instance, r. I can factor out r squared here, right? What is r squared? 600. 600. R1 is 100 squared times minus 1.5. Then we have 600 over R2. R2 is 200. Then square times 2. And finally,
Sir,
R squared over R3 squared. Yeah.
is it that 1 over 200, isn't it be
Uh-huh.
0.005?
1 over R2. You see here, R. This one is what? R is
It should,
600. R2 is 200, right?
I mean that the 1 over R2,
Uh-huh.
1 over R2 and 1 over R3, the value, is it correct?
Why?
Is it,
About the
isn't it be,
perimeter to find the
yeah,
value of
Oh,
R.
oh, I'm sorry. Yeah,
it
yeah,
is
yeah, yeah.
not the twice of the that
Mm-hmm.
one, yeah.
It's so. What is it?
0.005.
0.05. Yeah, yeah. You're right. Thank you. It's a
And then 1
mistake.
over 300 is
It's what?
0.003333.
It's approximately 0.0.
5.
0.05. Okay. 1 over
0.05.
300 is 3 over 100. 1/3 is 0.0333. Right. So approximately
Yeah.
like that. Huh? It's approximately.
The decimal places is 0.005 and also 0.0033.
Yeah. So what is it now? 0.033, isn't it? So what is the approximate value here? 0.09, right? 0.093, right? Approximately, yeah. 0.093. So what is R? You can use your calculator.
Sir, double zero, 0.005, not 0.05.
Okay, okay.
Yeah, it's the half of the first one, right?
Yeah,
So,
yeah, yeah. Yeah, you're right. 0.005.
And also 0.0033.
0033, yeah. So
so
if you use your calculator, what is it?
0.01833.
0.01833.
1833.
So what is R then? Approximately
54 something.
54.545454. Yeah, 5454.
54.
54. Approximately, yeah.
Then repeat. Repeat for
Okay,
it.
okay. So approximately, yeah. Yeah. So okay, yeah, I did a mistake. So this is what you need to. Okay, so this is approximately 54, 54 here. Yeah, 54, 54 over 300 times minus 1.5. Okay, please use your calculator to calculate all this. When you use your calculator, can you tell me? You can factor out, say, 54.
Negative 0.3471.
You can factor out this. So we have minus 1.5 here. We have 100 squared. This is 1 over 4, right? 104 times 2 plus 1 over 9 minus 1.5. Say it again.
Negative 0.3471.
3471. Yeah. So that means what? Is it increasing or decreasing?
Decreasing.
Yeah. It's decreasing. It's decreasing. Yeah. So the answer to the question, how fast is it increasing or it is decreasing? Yeah. So here R is decreasing. Okay. So these are three examples related to rate of change. Okay. Yeah. So rate of change is also covered in test 2 and test 1. Yeah. Any questions? I think three examples are enough here, right? Okay. So tomorrow will be uh, uh, the exam test will start at 9. Uh, starting at 8:30 p.m. I will give you the QR code for attendance. You need to go to WebEx, yeah, scan it, then until 8:55, 8:55, 5 minutes before the test, I will release you the test questions. Okay, test 1. But start answering at 9 p.m. Start answering at 9 p.m. And then you will work on the test 1 for 75 minutes. Okay, continuously. And then stop answering or stop writing at 10:15 p.m. Okay, and then you will be given 10 minutes, to compile all your solutions and scan them as a single PDF file. And then I want you to submit via e-learning. Yeah, I will create a portal for your test 1 submissions in the e-learning. Yeah, so and then so 10 minutes will be given. So make sure you do this within the time given here. So if e-learning fails, okay, you may submit directly to me through WhatsApp. Preferably, I want you to submit through e-learning. It makes my life easier. But if, however, e-learning fails, please submit it through directly to me through WhatsApp. Yeah. Okay. When you scan, please scan it clearly. You have submitted your assignment 1, assignment 2. Some of them are horrible. I have a difficulty because they looks very blurry sometimes, so it's difficult for me. So please make sure you scan the solutions clearly and use ballpoint pen, white paper. Yeah, you answer them your questions. Write your full name, matric number, and section on the top of your answer scripts. And then here is the Then when you submit, give your file a name. So this is an example here. Okay. 21. List name, full name, number. Okay, your name, section. I think 21 here refers to section. You should use 30, right? Section 30 then. Yeah. Then your name and then your matric number here. Okay. Any question? I will give this to you later on. And then, of course, this is online. It's an open book, but we expect students to be honest. There should be no discussion among yourselves. So for that reason, we want you to sign this integrity declaration form. Yeah? Write down your name, matric number, email, lecturer's name. Okay. So I hereby declare that the answer for test 1 was written by me and result of my own work. Okay. Then cheating or attempted cheating can result in expulsion. I promise that. Okay. So please sign this and then also submit this through e-learning. Okay. I will create a portal for you to submit this student integrity declaration form. Yeah. Any question? So I've given you some samples of test 1. So look at them to get some ideas. I But so far, the assignment that I've given you is about sketching graphs, a domain, partial derivatives. I didn't give you any assignment for the other topics. So so in the book there are many exercises. So try them on your own. Okay. I didn't give. I've given you assignments 1 and 2 related to surfaces, domain, range, and partial derivatives, but I did not give you any assignment related to increments and errors, chain rule, but I have given you lots of examples. Yeah. For 2 and 3 variables. Yeah. Okay, so look at the examples that I've given, try them out again. Look at the examples given in the book, try them out again. Also look at the try sums given in the, try them out. Yeah. Any question?
So far, so good, Doctor.
Okay, thank you. So now let me continue with double integrals. So I have discussed with you the concept of double integrals. Not this one. Not this one. Lecture notes. Double integrals. Double integral note 1. This is... No, not this one. These are double integrals. Yeah, this is what I have discussed with you last... is it Wednesday? Yeah, last Wednesday. Last week on Wednesday. Yeah. I've discussed with the concepts of double integral, then methods of evaluation of double integrals. First, we consider the rectangular domain. Yeah. Then it can be evaluated using this iterated integral, and then we look at non-rectangular domain as well, isn't it? Yeah. So what are the examples that I have given? Mm. Yeah, here then I gave you, then we work out some examples of evaluation of double integrals. Okay, sometimes a certain order is easier, right, to work for. Sometimes it is easier to evaluate double integral using a certain order. There are two orders, dx dy or dy dx. So sometimes one is easier than the other. Yeah. That also I've shown you some examples. And then this example where the region is not a domain. So this is not a rectangular domain. So this is a sample test problem. You are given a double integral using the order dy dx, but it is suggested here to change the order of integration into dx dy. So you need to find the appropriate bound for x and y. Yeah. So here is what we have discussed. Any questions so far related to double integral?
So far, I have no problems.
Okay. Mm, okay, let's see. In some cases, we have to split the integral. Yeah, yeah. In some cases, we have domain in this form here. So sometimes you cannot, if you have a domain in this form, there is no for here. You have a single formula for the lower bound, for the lower boundary here, y equal to gx. But the upper boundary, there is no single function to describe the upper boundary here. So you have to, there are two different functions for two different boundaries. So we have to split the integral 1 over domain d1, 1 over the integral over the domain d2. So let's discuss an example related to this case here. Evaluate this double integral 1 over x plus y dA with d as shown below. Okay, we have a region D here as shown here. Yeah. So we have the upper curve, the upper line has the equation x plus y equal to 2, while the lower line has the equation x plus y equal to 1. So that means the points here as shown here. Okay. So how do we evaluate this integral over such a domain D? So here we have to split the given domain D into two parts. Yeah. One way. Let me redraw this diagram again. So here we have the y-axis, the x-axis. So we need one way we split the domain into two parts here. Let's call it D1 and D2. Let's use the dots for D1. Okay. Yeah. So D here is equal to D1 plus D2. The region D1 is bounded by what? What are the bounds for D1? I can say x is between 0 and 1, right? For points on D1, x is bounded between 0 and 1, but y is bounded by the lower line. The lower line is, the upper line is what? We have x plus y equal to 2. So that means y is equal to 2 minus x, while the lower line, we are given x plus y equal to 1. So the lower line is y equal to 1 minus x. Okay, 1 minus x. So for D1, y is bounded below by 1 minus x and bounded above by 2 minus x. What are the bounds for D2? X is bounded between numbers 1 and 2, and y is bounded by the x-axis. Y is bounded by the x-axis, so it's 0, bounded above by the line y equal to 2 minus x. Yeah. So the integral, the given integral, we have to split it into two. From the bounds given, it is clear we need to use dy dx, right? Dy dx, the order dy dx, because y is bounded by curves, while x is bounded by numbers. And then for the second integral over d2, we also use the order dy dx, because y is bounded between curves and x is bounded between numbers. So let's do this one by one. First, we calculate the integral over d1. Okay, so the inner integral is with respect to y. Y is bounded below by 1 minus x and bounded above by 2 minus x, and x is bounded between 0 and 1. Okay, so first we evaluate, first we integrate with respect to y. What is the result? What is the integral of 1 over x plus y with respect to y? ln, right? Must be ln. X plus y. And this is to be evaluated at the endpoints. Yeah. So first we substitute y equal to 2 minus x. Yeah. First we substitute y equal to 2 minus x. Then we substitute y equal to 1 minus x. So we have ln2 minus ln1. Yeah. We have ln2 plus x cancel out, then minus ln1. Yeah. So it's just numbers here. And ln1 is 0. So we just have a single integral ln2 dx. The integral of ln2 dx is x between 0 and 1. So when x is 1, it is equal to ln2. When x is 0, it's 0. So that is the integral over L1 over D1. So now integrate over D2. No. Okay, so this you want to write down the limits for the double integral. Yeah. So take a look at D2 just now. D2 y is between 0 up to 2 minus x. While x is between 1 and 2. Okay. And proceed as before. First we integrate 1 over x plus y with respect to y to get ln plus y. This is to be evaluated at y equal to 0 and y equal to 2 minus x. So we substitute first y equal to 2 minus x. And then we substitute y equal to 0. So we get x plus 0 there. Dx. So now the double integral reduces to a single integral. And with integrand ln2 minus ln x dx. Okay, what is the integral? The integral of ln2 is ln2x because ln2 is a constant. What is the integral of ln x?
1 over x. 1 over x.
No.
1
No.
is wait. The table, right?
The integral of 1
1 over 1 plus x.
yeah. Maybe recall this integral formula of ln x dx is what? We have done this before. Is it not this? Right? We have done this before, right?
Maybe.
Yes. By integration by parts actually. It's not maybe, I'm certain. Yeah. I'm certain. Yeah. This is the integral for ln x. You can yeah, we have used this formula previously. This formula is obtained using integration by parts. Yeah. So let's just simply apply this formula. So we have minus, put a bracket there to avoid confusion. Yeah, ln x minus x. This is to be evaluated at 1 and 2. Put another bracket here. So first we replace x by 2. So we get ln 2 times 2 minus 2 ln 2 minus 2. And then we replace x by 1. So we get ln 2 times 1 minus 1 ln 1 minus 1. Okay. ln 1 is 0, right? ln 1 is 0. So 2l and 2 will cancel out, right? This will cancel out with this one. So 2, 2. Then minus what? ln1 is 0. So we have minus ln minus ln2 minus minus 1 is plus 1. So we get 2 minus 1 here. So it is 1 minus ln2. Okay, 1 minus ln2. So now we add the results. The integral over d1 plus the integral over d2. The integral over d1 is ln2, right? While the integral over d2 is 1 minus ln2. So ln2 cancel out, so the answer is 1. Yeah. So that's how we deal with this double integral over the given domain. So there's sometimes a student, when given this such problem, they didn't split it into two. So what's the common mistake? They write this integral as y between 1 minus x, y 2 minus x, and y x between 1 and 2. This is a common mistake, which is not true. Yeah, which is not true. This is wrong. So when you write it in this form, that means you are just dealing with a double integral. So there's no splitting, as which actually that which is actually required. Any question for this example? Let's look at another example. Mm. Determine the area bounded by the area bounded by the parabolas x equal to y squared, x equal to 32 minus y squared. Okay. Determine the area bounded by these two parabolas. So let's make a sketch of this. Let's make a sketch of the region bounded by these two parabolas. We have x in terms of y. Okay, we have x here in terms of y. X equal to y squared. It's a parabola that opens to the right, right? X equal to y squared. It's a parabola that opens to the right. Because x is always positive. Because x equal to y squared, so x is always positive. As x gets larger, x also gets larger. While the second parabola is a parabola that opens to the left. When y is 0, x is equal to 32. It is a parabola that opens to the yeah. So this doesn't have to be exact. I'm just doing a sketch here. So when y is 0, x here is 32. So the region is this shaded region here. Let's call it D. Okay, how to find the area? Remember, we can also calculate. You can solve this using your additional mathematics problem. So we can. But now we have studied double integral. You can also solve this using double integral. Let's apply double integral to solve this problem. So recall this. What we have discussed previously. Something to do with area. Which one is it? Yeah, I see. The area of region D is equal to the double integral of 1, okay, dA. So let's use this formula to solve that example.
Setiap hari, jom beli sekarang.
Kenapa perlu hadapi gigi sensitif? Tukar kepada Sensodyne hari ini.
Dream YouTube Studio.
Where is the
Best part
here.
about having a space completely desk setup. This
Okay.
is the most
Let's
important
recall
part
this
of the studio for me
this
because I
formula.
am not just a YouTuber. For my full-time job, I'm actually a professional filmmaker. I do videos for pro athletes all across the country, so I'm traveling a ton for that.
So the area of D is equal to the double integral of 1 dA over D. Yeah. Now, what order should we use? Dx dy or dy dx? What order should we use? You can see here, the region D is bounded on the left by this equation x equal to y squared, while it is bounded on the right by the equation x equal to 32 minus y squared. So remember this. Let's recall another thing here. To scroll down. Yeah, this is another possibility, right, for a domain D, which is bounded on the left by a function g with respect to y, bounded on the right by a function h of y. So if this is the case, then we need to use the order dx dy. We integrate with respect to x first, and then we integrate with respect to y. Okay, so the order that we need to use here, so d here, d, how to write the domain d, y, x is bounded on the left by y squared, and x is bounded on the right by 32 minus y squared. Okay, what about y? Y must the bound for y must be numbers. Okay, the bound for y here must be numbers. So y is the intersections. They are the intersection point of the two curves here. So let's call the as y1 here and y2. Okay, y1 and y2 are the y coordinates of the intersection points. Yeah, so we to find the bounds, we solve the equation y squared equal to 32 minus y squared. So that gives 2y squared equal to 32. Therefore, y squared equal to 16. So therefore, y equal to plus or minus 4. So that means y1 here is minus 4 and y2 is 4. Okay. So the bound for y is minus 4 and 4. So here is the reason. Here is the reason why. Okay, the calculation here. So now we evaluate this double integral using the order dx dy, where x is between y squared, 32 minus y squared is the upper limit, and x is between y is between minus 4 and 4. Okay, so the integral of 1 with respect to x is just x. Just x. And x bounded between y squared and x equal bounded the upper limit is 32 minus y squared. So first we replace x by 32 minus y squared, and then we replace x by y squared. Okay, so the result is so the integrand simplifies to 32 minus 2y squared. And it's easy for you to, I leave it to you to integrate this single integral, to evaluate the single integral and show that the result is 512 over 3. okay, because it is related to area, so we put a unit squared there. Any question? This example.
Sorry, the final answer is sorry, there is delay for me.
512 over. Okay. It takes time for you to arrive, huh? Using internet. Sometimes it takes time. Any question?
Doctor, is very clear for me. Very clear.
All right. What time is it now? It's 9:28. We didn't take a 10 minutes break, so I should end around 9:40. Yeah, 9:40. Any question? Okay, let's consider one question. This is related to finding volume. Find the volume under the plane z equal to 1 plus x plus y over the region bounded by the curves x equal to 1/2, x equal to 1, y equal to x squared, and y equal to 2x squared. Yeah, let's look at let's look at this. It's our weekly schedule here. Where are we now? We are now in week 6, right? Week
Yeah,
6, yeah.
week
No,
six.
no, yeah, week 6.
Week 6.
Yeah, but we are again behind schedule here. Double integrals in polar coordinates. Yeah, I will discuss this in our next meeting. Yeah, this Monday, Wednesday, I will discuss this double integrals in polar coordinates. But application of double integral, so I don't think we have time to cover this application. Maybe just one topic, maybe area, volume, but mass, center of mass, moments, we don't have time to discuss. This will, so according to the schedule, we need to discuss triple integrals next week. So in order to catch up with the schedule, can we have another makeup class next week? Can we have a makeup class again next week?
Which day?
Last time we did on
Sunday.
Monday, right? On Sunday?
It's Sunday.
I don't remember. Was it Sunday
Monday is okay
or
also.
Monday? Last time we did it on Monday, right? We did our. Am I right? on Sunday, yeah.
Sunday.
Yeah. So can we have another makeup class next Sunday, to catch up with the schedule at night time at 8:30? or 8:40. Yeah. Is it okay? So I will solve this problem next this on Wednesday. Um, so let's decide on this makeup class first. When? Next Sunday is what day? What date? What is the date for Sunday? Next Sunday, 25th, huh? 25th, yeah. 25th April. This is on Sunday. 8:30, Isyak 8:30. 8:40 lah, Boleh? Is it okay? Is it okay with everybody here?
Okay.
I'm okay, Doctor.
Alright,
Thank you, Doctor.
Okay, agreed then. Well, so, you know, we cannot go very fast, when we discuss these topics. I need to explain to you clearly, show you lots of examples, yeah. And also because we had 2 holidays, isn't it? On Tuesdays last time. So, okay. Okay, enough for our lecture today. So let me show you the QR code for your attendance.